I'm hoping everybody can see my screen as well. So, hello everyone. My name is Kenneth. I'm from HKN Outreach for UCLA. We are Honor Society for EE, and today's workshop we'll be talking about image compression, but we'll mainly talk about image compression with JPEG since it's the easiest one that we can actually understand. During this workshop, we're not going to be program intensive. It's just to show you what some of the libraries that we use and how we use those things, techniques, and then to actually visualize what's going on with JPEG or image compression itself. So without further ado, some preliminary actions will just be like mounting your drives, which is basically up here. Pretty sure it's already been mounted, so it's good. And importing my images that I may use. From there on, I'll install it in packages. So right now we'll be using OpenCV, which is CV2. There's some other ones, so like NumPy and MATLAB. They're just other programs from matrix stuff for programming from MATLAB. Okay. From MATLAB, so we'll use those because we could do 2x2 arrays and stuff like that. And then if you're trying to use CV2 or cv2.imshow on Google Colab, it won't work. You will have to actually import this area right here to actually make it work. And then this is just for me to open up images itself. So without further ado, let me explain about JPEG. JPEG stands for Joint Photographic Expert Group. JPEG and JPEG or JPG. During the 1990s, they had to abbreviate it to JPG because the suffix or the last 3 for x86 or for like Windows needed 3 digits or 3 letters. So you can't put JPEG, but I think in like Windows 10 now and higher versions of Windows, I think you're allowed to use more characters than that. So JPEG was founded in roughly around 1932, and the reason why actually let me go back. JPEG is not really a file format. It's a storage method. So when we talk about JPEG and how we do image compression, it's kind of a white lie. It's actually JFIF, which stands for JPEG File Interchange Format, which contains all the image data with the JPEG algorithm as well. And the standard publication right there is ITU tag T.871. So JPEG during the 1990s, internet speed wasn't that fast. It was probably at best like 1 megabits per second, maybe 10 megabits per second, the highest you could possibly do. But that's in the upper end. So most people will probably be in dial-up speed, which is like 40 to 50 kilobytes per second. And so if you ever go on like Internet Explorer and try to open up a page, there's a lot of images that you have to see. And if each image is like 50 kilobytes, let's say, it will actually take like a few minutes or even seconds to actually load up a single page itself, depending on how many images that they actually have and other important codes that they need. So, and that's the reason why they founded JPEG or JFIF format itself. So this is a little bit complicated, but for the most part, this is how, like if you look at a TXT file and then be able to look into it, you can actually see all these hexadecimals or just assembly language code that your computer actually takes in the input and uploads the image itself. So I'll be explaining, this isn't about creating JPEG application, but explaining what each portion is about, especially in these portion, which is quantization table, the Huffman table, and then the image data itself. So you already know that JPEG is a file format for images, but there's also PNG and TIFF files as well. And the difference between those two and JPEG is that JPEG is a lossy compression format, meaning that some data is lost when you convert it into a JPEG file, whereas PNG and TIFF are lost as compression formats. So whenever you're trying to deal with images that are like graphical and you need like actual all the points and data without any image loss, you actually use those. So if you're doing any type of like research or something, you don't normally use JPEG because some file will be lost and you'll see some artifacts in your JPEG files where PNG and TIFF will never normally don't have those. Another useful one is scalar vector graphics, SVGs, and the currently used preferred format for web design itself. So the step for JFIF or JPEG, so I'll be using interchangeably with JPEG and JFIF, so don't be confused with that. It's just how the name is. So JPEG starts from, we take an image, we separate the image into 3 colors or in 3 color spaces, which is RGB, and then we convert it into YCB, CRCB, and then we do some algorithmic applications right here, and then we quantize it, and then we store it back into the image, which this is the whole area right here. It's where we store the image back into the file, into that file itself, so that we can actually open it up later on. Any questions about this so far?
No question. What is the YCRCB thing you're talking about? Conversion?
Good question. So YCRCB, which I'll talk a little bit later, is Y stands for luma or luminosity. So the gradient with which how light or how bright or how dark the image is, which is basically black and white. And then CRCB stands for chromatic. So chromatic CR is chromatic red, CB is chromatic blue. And that's how we separate those images. So the idea was that we're using our human eye because our eyes are more perceptible with gradients of light, so we can actually conceive the what's called how bright or how dark the room is. But for CRCB, we actually don't actually see that well, and we don't actually see really closely. So if we try and look at different shades of red or different shades of green or different shades of blue, we won't be able to tell a difference if it's within like, if it's close to each other. So does that answer your question?
Yeah, that helps. Thank you.
Okay. So without further ado, we'll be using an original image. Let's just say it's Lena, for example, which is a standard image that we normally use. And then what we're going to do is we're going to run the code for CV2, which is IMRead, so that we could take in the image of the RGB image, because CV2.IMRead gives you the RGB colors. And from there on, we'll do some imaging. So we'll copy into what's this variable called blue, and we're going to filter out all the red and greens of that image. So we're going to set it to 0, similar with green and similar with red as well. And the result we get is right here. So this is for red, this is for green, and this is for blue. Now, if we try to take this image right now and store it into a JPEG file, what we have, number of bytes we will actually need is 512 times 512. Saying 1 pixel is considered 1 byte per se. So we need 512 times 512 times 3, which is a large amount of bytes, which is in the kilobyte range, if I remember correctly. So what we need to do is figure out what we can throw away, since JPEG is about lossy compression. So some data we don't need, and we could still preserve the image of itself, almost entirely 100% of the image. So from there, we actually use what we consider YCBCR. So for graphical string, this is what it looks like for chromatic red and chromatic blue when we set the luma to be half of at 0.5, which is 128. So RGB goes from 0 to 255. Similar with similarly with YCBCR, which is from 0 to 255. The scaling that we actually use right here is just a little bit weird because we can actually shift the number to negative 127 to 128, which is still 256 numbers. So that's what's going on. So if we increase it all the way up CR to 256 or 128, we'll see the red image right here if we set CB to 0. Similarly right here for that. And then if we set our CR to negative 127 or 0, for example, we actually see the green portion right here, and similar with the blue. So one way we can do it, so we got reduce the size of the image to do with 256 by 256. I'll explain the reason why we did that. But before that, we will actually take the image, convert the color of the image from RGB. So currently CV2 doesn't do RGB. So each block or each array is actually from blue, green, red. So if we go all the way up here, it's normally 3 matrices, but we condense it into 3 dimensionals. So just to be worried about that for OpenCV, when you try to do a read image with it, you just have to make sure it's flipped. So what we do is we take this image and this -1 is just to reverse it. So from BGR, it will be RGB instead. So we convert the color from BGR to YCRCB. And then we got to set our luma to be 128. The reason why we set it to 128 is that, let's see if I have it. If not, I'll explain. Oh, I don't have it. All right, because there's a way of changing the image, and it's based on basic computations with converting into RGB or YCRCB. It's just a few standard variables that standard constants that we use to convert it. And the result is this right here. So this is our black and white image, or luma per se, and this is our chromatic red. And this is our chromatic blue. And I'm doing the same thing. So CR is just, I'm making sure the Y portion and the CB portion is set at 128. Is there any question about the conversion from RGB to YCRCB or CBCR? If not, so we converted into YCRCB, but we still haven't figured out a way to compress the image, because these numbers will still be within 0 to 255 per se. So we're still in the same dilemma that we do, but what happens if some of the data, so we won't be able to do anything about it unless we actually change it to something else. So instead of looking at it spatially or in this image spatially in a 2-dimensional space, what happens if we just transform it into frequencies and look at it instead? So at lower frequency, it's bolder. At higher frequency of an image, we see those contrast. So like the image layouts, outlines that we see right here is basically higher frequency, whereas like images right here will be in low frequency. So what happens if we convert into two-dimensional frequency? Because one thing that we actually take for granted is that we don't actually see high frequency that well. We actually just do some little bit correction with our human eyes. So sometimes images itself, depending on how far you see it or how close you see it, how you zoom it, and you may see some pixelated images. So you may see some jagged lines, but for the most part, you may not be able to see it depending on how the image is compressed. So that's what we're gonna do is called lossy compression. And what this is basically converting into two-dimensional spatial domain into a two-dimensional frequency domain. This goes into, I don't know if anybody has taken differential equation, but it's similar to Fourier transform and Laplace transform. But for this workshop, you don't have to actually know about. We'll just implement the code or implement the image or the equation that we'll see in below. But essentially, we're converting into frequency domain and we're using a cosine. And the reason why it's called discrete and not just a cosine transform is that whenever you take image data or any data per se, like if you ever code in MATLAB, we don't actually do a continuous signal. We actually take it by a rate. So that, and it's impossible to do it continuously because it'll need infinite amount of energy, which is not possible. So this discrete code, that's why we call it discrete. And the goal is to actually, so this is a little bit complicated and I'll actually show a little bit image on how you can actually visualize it, but f of x or y is basically your block. So if we, let's see if I, no, I don't have it. So basically it's your image block. So at 0, 0 at the top left of your image, it will just be that whole one area of the pixel. And this f, right, capital F is basically our frequency at 0, 0. But I'll explain a little bit more what's going on. So the best way is to actually visualize it. So in a sense, if we look at u is equal to 0 and v equals to 0 at 0, 0, we'll see it. This is our image right here. And actually, let me go back a little bit more. So first, we have to actually take our image and break it into 8x8 blocks. The reason why we do it 8x8 is because it's faster computation, and the reason why we use number 8 is because in computer we use binary, so it's base 2. So anything 2 to the power is a lot efficient than, let's say, doing a 10 by 10 pixel itself. But you can also do that, but it'll be less efficiency as well. So that's the reason why we do 8x8. So we break it into 8x8 pixels for each block, and we do it for each block itself, discrete cosine transform. And the best way to actually visualize this is actually looking at this right here. So the brightness of this, if it's all white, is basically it's the maximum, which is a positive number. So at 0, 0, this cosine goes to 1 and this cosine goes to 1. And essentially you get this, and which is just taking all the images of all the blocks and then averaging it out later on. Don't worry about the scalar. That's for purposes for actually when you derive the equations, but don't worry about those. Those are just scalars, so you don't have to worry about it. So if we look at the next row or the next pixel, which is row 1, column 1, so our u is equal to 1 and v is equal to 0. This will still remain as 1, but u is actually, now we're seeing the cosine of it. So what we see is the brighter portion, which is the at cosine is equal at cosine at 0 angle. And the black portion is the -1 portion. So when your cosine is negative pi, we'll actually see the darker image of itself. And then similarly, if we go in the y direction, we're basically gonna set this to 0 and this as 1, and you'll see the same image in itself. And it's actually from top to bottom, which is bright to dark. And then when you actually get into between, you actually mix those two, and then you'll see some different types of images like that we see right here. I know this is a little bit complicated, but does anybody have any questions about this so far?
And this might be like a really simple question, but is this just used to basically generate or is to compress images through like coding?
This is one portion of it, but right now we're doing is we're taking something in time domain and covering it to frequency domain, because in time domain we can't do really, or in spatial domain we can't do anything to each pixel individually, because one, it'll be complicated, and two, it'll just be hard computation wise, and there's not much we can do to standardize it. But in frequency, like I mentioned, that higher frequency is basically your edges, or like if you actually see like a text file or like a character or like image that has characters in it, those sharp lines are basically high frequency itself. And what we're trying to do is separate all the frequencies out and putting it into an 8x8 block. Does that answer, or do you need more explanation?
No, that answered it. Thank you.
Yeah. So don't worry about this formula and how it's derived. You'll probably learn this Fourier transform or Laplace transform Fourier series about it, but it's basically using this and then actually trying to do something with it. So right now we're gonna take this partition. So we're gonna partition our image from 96 to 144. So that we can actually see our linear picture, and it's around here. The reason why I did it right here is because there's a lot of sharp edges and there's a lot of spaces right there. And what we do is just same thing, we cover it. And then what we have right here are considered quantization tables, which I'll actually explain why we have those quantization tables. But basically these are just numbers that we'll be using. And in this portion, we're going to be going by 8x8. So this is the block itself. So we try to get the length and the row of the column of our image. And then we're going to basically create empty arrays so that it's more efficient. And then from there, we're going to convert it into floats, because right now our pixels for each block or each element are in integers. However, if you look above this equation, this actually deals with basically decimals. So we actually have to convert it into float so that we don't lose data when we actually get those back. And basically we're gonna divide it by 8. So that's the reason why I did 256 by 256, is because it's easily divisible by 8. And from there on, we basically get our row, get our column, and basically these are our blocks. So there are in total 6 row blocks and 6 column blocks. Right, in each, so 6 times 6, it's 36 blocks that we have to go through. So from here, we actually use what we call the CV2 DCT program, which is basically CV2 is how they implement the equation above. And basically, we're gonna use that, and we're gonna take the image, and we're gonna store it into a quantized, basically we're gonna take a DCT and we're gonna now quantize it. So what quantizing does is basically we're just dividing that table that I showed you right here, dividing it by the DCT. So if we look down right here, we have the original matrix. We're gonna take that quantized table and divide each element by with each block. So 794 divided by 16 will be roughly around 50 after rounding it. So what we will do is round it a little bit afterwards, which is right here. So we're gonna divide it and then basically round it a little bit later on. But for now, basically this is all we do for the DCT portion. And what we notice is that we typically keep our higher frequency or our lower frequency, but we discard all our high frequency, and we'll see what happens when we do that a little bit later. But once we do that, we want to convert it back into our spatial domain so that we can actually see it. So this later half of the portion is basically we're going to convert it back to into spatial domain, which is what we see right here. And what we call this is the inverse discrete cosine transform. Basically taking our frequency of our blocks and then converting it back into spatial and 2D spatial domain. So from there on, we basically, this is what's going on. We have the original, we divide it by the quantization table. And then prior to that, we actually multiply it back with our quantization table, which is basically taking that block right here and just multiplying it right here as well. So 50 times, what was it, 16, will get you 800 roughly for take. But since we're rounding it, you guys see some rounding errors like what we see. So this is what happens after we do the DCT matrix, after multiplying the Q table. So this is what's going on, 794, 800. So there's some rounding errors that we have. So that portion is where we have some data loss as well. But then we also see that all basically high frequency is basically still lost. And actually, I'm getting myself confused right there. Actually, this is our before. So this is our quantized for luminosity, which is basically from 0 to 255. And when we did all that information right here and then go back into our DCT format, this is what or back into our spatial domain, this is what we get back. So you can see some little discrepancies, so like 135 and 136 and 443. And then if you look around here, there's some like rounding, there's some like differences between it. And that can actually affect your image depending on basically your quantization table is. So what we're gonna do is, this is still the same idea that is above, but so what we see is that this is our original image in black and white. So we're doing it only on luminosity, and we can also do it in chromatic and as well, but we're gonna just focus on it. And what we see is some image discrepancies. So we see that basically up right here, you'll see some like jagged edges right here, which we lose some resolution because of that. And we can see it when we zoom into the image itself. But let's say if I want to look at it by 256 by 256, I'm sorry, my dog is probably barking at the mailman right now. So instead, what we can do is basically do a DCT of this whole image right here. Run the same code again. Let's get a little bit portion there here. And what we see is almost the practical image of itself. Like this is the original image, and this is what happens after we basically did the quantization table and then revert it back and then try opening that image again. Is there any questions about this so far? So basically what we could do now is, since we know we could see it in luminosity, now we can actually do it for chromatic red and chromatic blue, which will actually alter the coloring of the image. But however, since we don't perceive the colorings that well, we can't tell the difference between shades of red if it's really close together. There could be harsher penalties. So when we look at our quantization table, what we can see is that these higher numbers right here is basically trying to get rid of the higher frequencies. So for a CRCB, we can actually increase the image right here and actually basically take up more of the higher frequency away from it. And what we get is basically this image right here. So we're going to take an image of Goldie and we're basically going to convert it. So when I did the code for this, it's lum 50. So we're doing 50%. So half of the 50% of the image quality is basically reduced to by 50%. And basically we're going to look at what happens to this golden retriever. So this is the original image, and I want you to pay close attention to the edges right here and basically hits fur lines right here and see if it actually changes or not. This is for 80%. And I can't tell any difference between that. And basically this is 60%. And we could start seeing some little artifacts, some little jagged edges. Not so much. We can't tell the difference unless we zoom in, or if we focus it on itself. But if we keep going to 40%, not that much change. 20%, a little bit of change, but once, and you can see it right here a little bit more. But if you see 10%, so basically 90% of the image data is lost. What we basically see is a lot of artifacts that we see, some pixelated images right here, and that's what's going on. So the reason why we do this is so that we get a bunch of zeros, and that's our goal. And what we do is when we store these data, we want to store it in such a way that we don't store each block basically by like 0 to 125, which takes up 1 byte. But instead, we want to actually take each block and basically store these amount. And then basically, this is all zeros. And what we can do is basically put all the zeros at the end of our data file. So when we actually encode this, we actually read from in the zigzag formation. So right here, we go from 800. Actually, my apologies. This is what we actually store into the data right here. Is basically restoring the 50, restoring the 5, -1, or 5, we go to 12. We store from we store 5, 1, -1, 0, 3, -1, 1, and you basically keep going on. And what you see is that there's a lot of zeros at the end. And what we could do with all those zeros, we can actually compress those zeros into a smaller format, which I'll explain how we do that a little bit later on. But for now, I want to actually show you a video by Tom Scott that he actually explains what's going on much more in depth. Okay. Thank you, Tom Scott. So basically, that's how you're supposed to do it. So the reason why we convert it to a lot of zeros right there is basically so that we can actually take all those zeros and basically put it in like a Huffman tree that he explained right there, which is basically if you haven't taken in higher CS classes, you'll actually learn what a binary tree is. It's just a data structure where we store information in. So basically what we do is basically we store all these zeros right here. And then basically we put it on the top of the area so that we can easily access them really quickly and efficiently. And since we only need 1 bit to actually represent all these zeros, most likely, it's a lot quicker, and we can store it, or 1 bit, not byte. So 1 byte is 8 bits. So we can actually store those in 1 bits, most likely. And basically for like -1, 2s, you see 2s, -3, you'll be to the right, so you'll actually transverse it a little bit more, which is probably maybe take 2 or 3 bits or even more. And the less frequent ones are basically like the higher numbers, like 50, 12. You'll probably take a little bit more, but which is fine. But the end result, what we get is basically this right here. So we print out the image, how much kilobytes it actually takes. So we take the original image, which is basically right here, which is 40 kilobytes, and we compress it down to 60%, which is basically we see a 43 kilobytes. So there's probably a difference between 6 kilobytes. Compress it down to 40%, you'll see a decrease by half. And then we keep doing this, and basically we're reducing the image. But we notice that at 10%, we see some artifacts. So we probably may not use 10%, but we may use like something like 20% or basically 40% for our image. So that's what's going on. That's how we compress the images as that. So does anybody have any question about the Huffman tree and Huffman coding?
No, I like the video though.
Thank you. So that's what's going on right here. So the quantization tables, these two quantization tables, to sum it up, is basically one is for your luminosity and the other one is your chromatics. So for those, we fill in those tables because these tables are not standardized. Basically, I can actually go up there and change some numbers and we'll get some different results. And each different results, we'll get something else. And if I remember correctly, almost any brand of sorts actually has your own quantization table that you can actually go through right here. All these information or all this will be on the reference link on the bottoms, and you can actually look it up later. Down below. So that's what they are. And the Huffman tables is basically our zeros and ones, basically how we store it. For basically there's 4 portions, but I'll explain a little bit reason why in the bottom image, but that's how the Huffman tables are. And the image data itself is basically the Huffman tables are the Huffman trees, and the image data is basically the zeros and one, how you traverse basically the Huffman tree itself to get your image back to that code. And the reason why we do it in 4 Huffman table is because we want to separate the DC portion, which is basically when our frequency is 0, 0, or basically the top left portion, and separate into a different table. And the reason why we do this is because typically DC, as you notice above, is really high number, like 50 or 70 or something of that high. So we want to store it somewhere else because the AC portion is basically the other 63 blocks or 63 pixels are basically low numbers. So what we want to do is store them differently so that we can actually do that. And that's the reason why we actually have that. And there's a little bit difference between what these PCM and run life code, but we're running a little bit of time and it's a little bit complicated. But basically, run life code is instead of like storing a bunch of zeros, what we could do is just say how many zeros are there, keep that information, and then basically say this image has this 0 and had this amount of zeros. The size of the zero of the running length. That's the reason why we're doing zigzag, because there is a trailing edge of zeros. Basically, take those whole zeros and basically count the size of it and basically give it a new unique identifier that this is 0. And that's the reason why we have some lossy. That's why we actually use JPEG in the earlier days with web design or websites and web designs, because we can actually compress those images and down into by like 50% and still not lose our image quality. And that explains what JPEG is. And the reason why it's called a lossy compression is because we lose some data, especially in a higher frequency. So that's the reason why we had those dragging edges. And the compression portion is basically can be the arithmetic, the Huffman coding or the Huffman table or Huffman tree itself. That concludes this workshop. Is there anybody have any questions of sorts? If not, I'll list all these references that you can use. So there's OpenCV library, which you can open up and actually figure out how these function works. I also linked the JPEG standard publication. The reason why we use 8x8 or the power 2 for coding and efficiency, the derivation for DCT, if you're interested in the mathematical portion, how we get to that. You may need a little bit of understanding of DFT, but if you let's say you just want to see how you get from DFT to DCT, discrete Fourier transform or Fourier transform into cosine transform. That's how it goes from there. And then Huffman coding and Huffman tree, since it's really standardized, you can easily find a Huffman code and Huffman tree and actually just take it from there itself. If you want more information about that, you can look through that. And then Wikipedia actually explained basically the numbers that we actually go from. So if we look at the bottom right here, basically we're taking our red, green, and blue and multiplying to a constant, adding it up together. And that's the reason why we get how we compare it to YCVR. And if you want to back to RGB, we actually do it right here as well. And that concludes this workshop. Thank you.